law states that the current flowing through a resistor is proportional to the voltage applied. More voltage implies more current. The voltage V is equal to the product of current I times resistance R. V equals IR. A plot of voltage versus current yields a straight line with a slope equal to the resistance R. Resistors are marked with 3 color bands and a 4th precision band. Each of the 3 color bands represents a digit from 0 through 9, with black representing 0, brown representing 1, then the rainbow of colors, Roy G. Biv, ending with gray and white representing 8 and 9 respectively. The first 2 colors form a 2-digit number which is to be multiplied by 10 raised to the power of the 3rd color. If the isolated color band is gold, the precision is plus or minus 5%. If it is silver, the precision is only plus or minus 10%. As an example, the resistor shown in the picture above has brown, black, red, and gold. This indicates a resistance of 10, 10, times 10 raised to the 2nd power, or 1,000 ohms, with a precision of 5%. Since resistors are not very accurately made, we should always use measured values for analysis purposes. The circuit boards have rows consisting of 4 holes in contact with one another, with gaps that are not connected. Long rows are also connected along the long sides of the board. Resistors are placed in the circuit board bridging the gap, and external connecting wires are placed in the same row as a resistor lead to make contact. We begin by measuring each resistance using the multimeter as an ohm meter. Place a resistor in the circuit board bridging a gap. Connect the black common hole of the meter to one end of the resistor and connect the red volt-ohm hole of the meter to the other end of the resistor. Turn the multimeter dial to about 10 o'clock where it becomes an ohm meter. The most accurate dial setting is the minimal setting that still allows a resistance reading. Compare the measured resistances with the labeled resistance indicated by the color bands. Now we set up for the Ohm's law experiment. Place the resistor, about 1,000 ohms, in the circuit board bridging a gap. The multimeter on the left is used as an ammeter to measure current. Run a lead from the low voltage terminal of the power source to the common hole of the ammeter. Make the connection from the amp hole of the ammeter to one side of the resistor. In this way, all the current running through the circuit must pass through the ammeter. Now connect the high voltage side of the power supply to the other side of the resistor. The multimeter to the right will be used as a voltmeter and is placed with leads sampling the voltage on either side of the resistor to record the voltage drop. Notice that the red and black holes of the voltmeter are used. Turn the dial on the voltmeter to the 20 volt maximum range at about 2 o'clock. Turn the dial on the ammeter to the 20 milliamp range at about 7 o'clock. Switch these meters on. Turn the 2 voltage knobs of the voltage source to 0, and then turn on the power supply. Ease up the voltage until the current reads 2 milliamps. Take readings of both voltage and current. Repeat the measurements of voltage for currents of 4, 6, 8, and 10 milliamps. We have used graphical analysis to make a plot of voltage versus current. A linear fit to the data yields a slope nearly equal to our measured resistance. The strategy in this next section is to keep the voltage fixed at 10 volts and substitute different values of resistance to see what current results. A graph of current versus the inverse of R should be a straight line with a slope equal to the constant 10 volts. Turn the voltage to precisely 10 volts and measure the current. Then swap resistors, keep the voltage at 10 volts, and measure the new current. Make a plot of I versus the inverse of R. Make certain that you use the measured values of resistance, not the color band value, which could be very inaccurate. Here the slope is found to be 10, and the correlation coefficient is very close to 1.0. A device such as a water heater is attached to a well-known voltage source, say 110 volts or 220 volts. Thus, by measuring the resistance of the device, we can use V squared over R to determine the electrical power usage, the energy consumption of the device over time, and the cost of its operation.